Hey there, everyone. Welcome to my channel. My name is Ryan Schul. I've got a really cool teaching lesson for everybody today. I'm actually very pumped about this one. This is all about bike rental demand forecasting. We are going to look at City Bike, um, the City Bike system that is distributed all around New York City, and it consists of hundreds of different locations where you can pick up and drop off rental bikes, right, for tourists to get around the city or for commuters to get to and from their origin and their destination, right, and probably everything in between that. Those are the two primary markets, but there's probably some some markets too. Okay, so why would we even be interested in analyzing data like this? It sounds like it's almost like a non sequitur, right? But not really. If we understand this type of analysis, we can actually optimize resource allocation. If we work for Citibank, we can improve customer satisfaction by making sure that bikes are available at different locations. I'll get into that in just a little bit. Cost efficiency and profit maximization, obviously for Citibank, right? Urban planning and infrastructure development, that's a big one. Sustainability goals, I'm going to talk about that a little bit in just a bit here. Competition and market positioning, seasonality and market-based demand, predictive maintenance, right? Any kind of maintenance that has to be done for the bikes to restore them into good order or to keep them in good order, right? Um, Predictive maintenance, data-driven decision making. Of course, all of our decisions should be driven by data and some intuition too, but not gut instinct, right? It should be driven more by data than anything else. Financial forecasting and budgeting, and perhaps other things as well. We can try to tease out a few other possibilities as we go through the analysis today. So I got some feedback that my videos were dragging on, and I was just talking ad nauseum about all kinds of things that sometimes don't even really have any relevance to the topic. So I'm going to try to keep it short and crisp and on point today. Okay. So I got the data from here. This is 2024-07. So that sounds like July. Sounds like July to me. I found the data over here. If I do Control F, you can find that file right here. Okay. There's actually two. First time I made a mistake. I got this is Jersey City, I think. When they plotted it on the map, I saw everything in Jersey City. So I guess JC is Jersey City, and the other one is for New York City. Okay, so make sure you get the right one. If you're in Jersey, maybe you want Jersey. I actually wanted New York. I got the wrong one by accident, but yeah, I corrected that and refactored that and got back on track here. So here's the data when we import it. So we see the ride ID. So everyone has a unique ID, right? We have the start point. I'm sorry, the start time. So you have the month, day, year, and then the time of the day, right? So that's important. We have the station name where we're starting, station ID. Personally, I think the station name is more important. I'll show you why in just a bit. Station ending name, and then we have things like latitude, longitude, which is pretty cool. And we're going to do some feature engineering. So we're going to take this start date and end date and parse that into a bunch of different pieces. So we're going to get the year, the month, and then the day, and then the hour of the day, and then the day of the week spelled out: Sunday, Monday, Tuesday, Wednesday, so on and so forth. Okay, so let me delete that. That was something I was looking at before, but I don't need it now. So when we go ahead and extract the data using some data engineering techniques, we can go ahead and get the features looking like this. So start hour is 21, start day is 1, and start month is 7. So we look at July 1, 9 p.m. Looks like 9 p.m. And that's exactly what we see here. So 9 p.m. Almost right in the dot. And this is July 1st. Okay, so that's where we get these feature engineering things set up over here. And then we have the start of day, morning, evening, afternoon, and so on and so forth. And look at the code. I'm not going to take you through every step. This should be pretty intuitive. If it's not, you know, take a look at it, spend some time. It should make sense pretty quickly and pretty intuitively. But if not, go ahead and take some time. I don't want to spend a whole lot of time, right? I'm trying to keep the videos a little bit shorter than they have been in the past. Some of them have dragged on and on. One actually went over an hour, believe it or not. That was not one of the most popular videos. So I can tell by people's response just clicking and watching the video, that's not what people are looking for. So I'm going to try to keep it on point here. Okay, so take a look at the code at your leisure. I'm going to share all this code with you so you don't have to write it down or try to take notes or try to understand everything in real time. You can have as much time as you want. Once you download the code from Google Drive, I'll post the code to Google Drive and I'll post a video on YouTube in just a bit here. Okay. So in this case, we're looking at the start hour and the rideable type. So we have the hours through the day. 0 is basically midnight. 1, this is 1 a.m., 2, 3, or 4, 5. So it dips down here. Not too many people on city bikes at 4 and 5 a.m., but it definitely peaks up here around the commute time. People are coming into work. Then 10, 11, 12, 13, 14, 15. So 15 obviously is 3 p.m. And then it kind of peaks at 1600 hours, right? People are cutting out of work just a little bit early and starting their evening commute and going back, and it's kind of dipping down. And you see this pattern over and over. This is the average based on the hour per day. And you can see by e-bike and classic bike, these are Plotly charts. So you can zoom in and see all the extreme details if you need to. It's kind of obvious, I think, in this view. You don't have to zoom in. And you see the numbers on the bars when you put the mouse over it. So you can see electric, classic bike. Here's another view instead of by time of day, by day of the week. So you can see it kind of peaks, it kind of ramps up and peaks on Wednesday, and ridership is down a little bit Thursday, Friday, Saturday, Sunday. Must be more tourists. Probably not too many people going to work, but maybe there's a few. Now, this is just July data, so this kind of peaks over here. This chart isn't necessarily useful right here. I included it just to validate that we're looking at July data. It's pretty much all we're going to get out of that. So now we can go ahead and set up some machine learning exercises and go ahead and try to understand what is the demand for bikes, what's it's been in the past, and then what is it going to be into the future. And there's a lot of things we can look at. The day of the week, we saw that. The hour of the day, we saw that. The month of the year is only July, right? We don't have lots of months of the year. I'd imagine in the wintertime when it's freezing cold, it's going to dip down maybe in the middle of summer. If it's blazing hot, ridership might dip down a little bit, but those would be kind of the outliers or the anomaly types of months. I would expect most of them to be pretty consistent. But again, all we have is this 1 month. But I didn't see other dates over here. I could go ahead and download these other dates. I see here's January, February, March, April, May, June, July, right through November, December down there. I'll show you how to do that later. I actually did not undertake that exercise because the data sets got so big. It was crashing my system, and I really can run it on a laptop. If you have a large processing system with a lot of clusters, maybe Databricks, for instance, you can do this analysis pretty easy. I'll show you basically how to do that, but on my system, it just didn't work. You can see there's already 1, 2, 3, there's already a million rows here, right? So it's getting up there. It's not too much for Python, but on an older laptop like I have, it's a lot, guys. It's a lot, kind of stressed out the system. So here's the regression algorithm that I chose, random forest regressor. You can choose the regressor. This has to be a regression problem because this is numeric data. We're trying to predict number of bikes demanded, right? That's what this whole analysis is about, bike rental demand. So if it's numeric, it has to be a regression type of problem. If it's a labeled type of scenario, then it's a classification problem, right? This is a regression problem. So I go ahead and set the regressor over here, do the training, testing, fitting. I fit the model right over here. Okay, regressor not fit, and I get a pretty nice R score of 0.9999. So the data is in good shape. It's clean. The model is learning, and it's able to understand all the nuances of the data. So it's learning, the details without overlearning and overfitting. Presumably, I didn't do an overfit test here, but I think we're fine. I think we're safe. That could be an extra step. If you want peace of mind, you could do that. Overfitting type of analysis. I don't think that's a problem here, although the R squared is a little bit high. But this exercise is not about testing for overfitting, so I'm going to avoid that. There's all kinds of directions we can go. I did a bunch of analysis here, just not that specific one. Okay, so we got high R squared. This looks like we're in good shape. I'm very optimistic here with this, and we can go ahead and start to make a prediction based on historical numbers. So we know, based on the past, we know the start hour. I'm just picking a random hour here. 8 is 8 o'clock in the morning. This is a weekday, not a weekend. And this is the start month of September. I'm sorry, did I say September? Sorry about that. This is July. I don't know why I said September. So July is the 7th month. You see a 6 over here because it's 0 based. So it starts 0, 1, 2, 3, 4, 5, 6. 7th month. This is July that we're looking at. And again, 8 o'clock in the morning on a weekday in July. We don't have all the dates or all the months of the year because it just wouldn't work on my notebook. But anyways, aside from that, like I think the analysis is pretty decent. It's pretty bulletproof. Okay, so we can look at this demand in the entire ecosystem at 8 a.m. on a given Monday in June. This is July. Sorry, keep on saying the wrong thing there, right? Let me just double check this. Why am I getting confused here? 0407. That is July. Okay, so the 6 is the 6 month after zero base rate. That's how we get to July. So that is fine. Let's predict the demand per station, and this can allow us to make a minimum number of bikes per station and make sure that we have this minimum number so we don't have too many bikes at the station and people are using it, or we have too few and people can't get a bike when they need a bike. Okay. Now this type of demand is for the entire system right here. Okay. At this point. So around 8 o'clock on a weekday in July of 2024, this was the data that we fed in, and these are the predictions that we're making. So 10,056 bikes are in use. That's a lot of bikes, guys, but that's a very big system, and there's a lot of people in New York City. So I think that drives. I think that makes sense. Just quick sanity check. That makes sense to me. But that's a big system. So we have 10,000 bikes that are being demanded at any given point around 8 o'clock on a Monday morning. But let's try to get that a little bit more precise. How can you find out like exactly which bikes are going to be used at which stations? Because 10,000 a lot, and if I have to make a guess, I'm probably going to guess wrong. I want a little bit more insight into how we can expect demand to either wane, wax or wane, or increase or decrease or whatever, given different stations around the city. So this is the demand for the entire system, right? But I want to know station by station how that's going to work out. So I'm going to encode the station right here. This is going to be station coded. If you look here, start station name actually comes from up here. If we go back here, start station name is this guy right here. Okay, start station name. So West 24th Street and 7th Avenue, Park Place in Buffalo, East 48th, Melrose Avenue, and West 24th and 7th again. Okay, so that guy shows up twice on 5 records. That's nice. So that is fine, but we have to take that name and convert that to a number. So we're going to encode the data. There's at least 3 ways to do this. You can use one-hot encoding, you can use categorical encoding, or you can use label encoding. We're using label encoding. I have a preference for that. And there's different scenarios where you would use different ones. I have a whole video on that. You can look at that on my channel. The video is all about different types of encoding tactics or strategies and why you would use either one or another. In this case, we're using label encoding. So we have the same kind of convention that we had before, random forest regressor. We are going to fit the model right here, use it to make predictions. Here's the Y predict. And again, we get pretty decent R score, not quite as good as we saw before. I think the last one was 0.9999. Now we have 0.993. So slightly less accurate prediction, but still very decent. Anything high 0.9 is totally fine. We're happy with that. Okay. So we have to label encode non-numerics. That's why you just mentioned. After making predictions, we can use the label encoder to do an inverse transform to get back to the original name that we had. So we convert from the name to a number. We convert that number back into a name just so it's easy to interpret. Because if I say station 1, 2, 3, 4, 5, 6, I don't know if you're going to know what that means. I don't even know if I even know what that means, right? But if I encode it into a number over here, right, this station data frame, station encoded, this is a number from 1 to whatever the number of stations go up to. But we have to get that back into a name realistically to be able to share this with stakeholders and to really make sense of that. If I had station 1, 2, 3, 4, 5, 6, that doesn't have a lot of meaning. This means a lot more to me and probably to you too, right? So we have East 72nd. The demand is going to be about 48 bikes around 8 a.m. on any given Monday morning in the summertime. Again, we're looking at July, but it could be June, July, August, anything like that. Probably a little bit different demand from dead of winter. It's probably going to dip down a little bit. So the season is important, and the day of the week is important, and the time of the day is important too, right? All these factors have to be considered. So we're saying this station, 48 bikes. Here we have 48, 43, 40, and it's no accident it's going in descending order. I set this to ascending equals false, so by default it goes to descending. I'm looking at the top 50, so we don't have to get 500 different bike stations here, okay? So these are the most popular bike stations any given Monday morning around 9 a.m. So I started to print some stations here. Actually, I don't even need that. I'm going to cut that out. And again, I'm going to share this code with you, so I'm cleaning up a little bit as I go through this thing. Okay, I wanted at this point to create a heat map so we can see visually how many bikes are demanded. Here we can see hour of the day. So 16 is 4 p.m., 17 is 5 p.m. Okay, this is military time now. I guess we can convert that pretty easily to 12 hours AM, 12-hour PM, but by default, I think it comes in military time, and that's fine. We can live with that. So the ride count is 16,725. That's a lot. That's a lot. Now we're looking at Saturday, and this is 5 p.m. on a Saturday. 5 a.m. It's actually kind of busy too. At 8 o'clock in the morning, 11,000 over here. That's a kind of peak, 16,725, 14. So the colors are a little bit lighter. You can see the darkest one is here. Dark corresponds to a higher number, light corresponds to a lower number. That's pretty intuitive, right? You have the key on the right, or the what's the thing I always forget the name of that. The user key or the key, I don't know. The color bar here on the right, I forgot what it's called. Oh, legend. I guess it's a legend, right? Who came up with that name? But anyways, so we have the legend and we have the lighter and darker spots corresponding to higher or lower frequencies of bike utilization, right? So at this point, I want to go ahead and take a smaller subsample. I'm taking 15% of the whole population, and I'm going to go ahead and plot this right here on this map. Let me hit Control Enter to refresh the view. Just to make it a little bit bigger, I put the width in there, the height and width. I like to see that just so it kind of blows up a little bit bigger because it was kind of shrunken down a little bit. Okay, so we have the view now, and you can see the darker red corresponds to higher demand or higher count, okay? And the light blue is kind of in between, and the dark blue is lower, right? So you can see by the shades, I think this is called, what is this saying? Oh, Ice and Fire. Very creative names, by the way. Like Legend and Ice and Fire. Whoever comes up with this, I applaud you. I really do. So this is Ice and Fire. And if we move the map around a little bit, we can kind of mouse over it. That's why I love these Plotly charts. It's showing us longitude, latitude, count of 1. That's a pretty big circle. I don't think that's a count. I think it's something else. Get over there, kind of like have to just finagle the thing right on top of it. Count 1,402. Here's a bigger number, right? This red is 1163, and then 1156, so 1,156. Again, darker colors, darker reds correspond to higher numbers, darker blues, lower numbers, and the lighter colors are in between, right? And we're looking at, again, the start and the end, latitude, longitude, right? There's the starts, there's the end. So that shows us the geolocations around the city and around Queens and around Brooklyn too. And we're basically counting, or over here you can see we're counting the latitude and longitude and taking a sum of all of the items too. So you can see the count shows up here, okay? And the sum is actually used, I don't think we're using a sum. I think we're doing two aggregations, a count and sum, and we're actually only using a count. I think it makes more sense. We're counting the number of bikes. If we're summing it, that could be useful in other scenarios. I don't think that makes a whole lot of sense for this particular view right here. Okay, so I'm just checking the time, trying to keep the video kind of short as much as I can, but still cover the material that I want to get through here. So at this point, I was almost ready to close the chapter and start creating the narration here, which I'm doing right now. But then I realized that Citi Bike actually has a real-time live API endpoint with real-time data. So this is super cool, guys. I went to this over here, pulled down this JSON string. Now, sometimes you can see this. I didn't even look at it. I just found this online. Let me see if I can view this thing. Sometimes you could just fetch the JSON. Sometimes they actually expose it. Oh, yeah, so they do expose this one. So you can see here's the JSON string. Not very reader-friendly for a human, but for a machine, very useful, right? Very condensed, compact. You can extract that. You can fetch it very easily and then convert that into columns and frames when we deconstruct that JSON that's all packed up, right? Once we unpack it, we can see in real time all the station information. And I like this a lot because it actually has capacity per station. So the original data set that I showed you, the CSV they imported from July, did not have the capacity. And I was thinking, like, how do you get the capacity? Because I've seen these things. Like, I wouldn't know, and it's not given to me in that CSV data, but somehow it has to be out there. Like, somebody knows, and I searched around, and I found it at that API endpoint. So that was a jackpot when I found that. I hit the jackpot. So I got the capacity over there. Has some other things, latitude, longitude, station ID. What else? Station name, we had that in the original data set, so that's fine. External ID, rental methods. I don't think we had that originally. I'm not necessarily using that, but that could be helpful for some things. Rental iOS, so on and so forth, is returning number of docks disabled. Okay, so this sounds like broken docks and number of e-bikes available. That's useful too. Okay, some of these have more e-bikes, some of them have few. I've seen a lot of these stations have none, but people I think tend to prefer the e-bike. You could just hit the button and just go. With the other bike, you have to pedal. You actually have to do some effort. I think people like the e-bikes. And then is installed is rented. Number of bikes disabled. That sounds like broken to me. Number of bikes available. So this is a jackpot for two reasons. We have the number of slots available that I just showed you over here. This is capacity, right? Those are the number of bikes that totally can fit into that location when they're all docked in the docking station, and number of bikes available. So you can have an array of bikes, 20, 25, 30, whatever the thing is, but maybe there's none available. So those bikes need that bike rack, whatever the thing is called, needs to be replenished if it's zero, right? And this is real time, so it's pretty nice. So hopefully, who's ever running the show over there at Citibank or City Bikes, whatever it's called, they're on top of this, and they probably have like a threshold. If the bikes get below a certain number, we send out some workers. We roll a truck with a crew to deliver some bikes if the capacity is down to zero, right? Because nobody can rent the bike, right? So this is a jackpot really for two things, I think. For this right here and for this, because it did not come in the original capacity, did not come in the original data set. But I can take the original data set and merge it with this. Now I can blend these together and I have more data, and I can make more detailed, more informed decisions that help me and help the community of bike renters here, okay? So I go ahead. This is pretty common. I've done this in lots of my videos. We have the first data frame. We have the second data frame. The first one is on the left, so the left comes first. The second one's on the right. We're merging on station name down here. And then on the second name of the data frame is name. If you look over here, there's the name. Okay, so station name and name should match up. And we're doing the left join to get everything from the station's data frame. So this has all of these details. This is the station's DF on the left. I'm sorry. Station's demand on the left, okay, because this one comes first. So left is first, right is second. Station's DF is on the right. And we're doing the left join just to make sure everything on the left data frame is matching up and all the matches on the right match up. But if we're missing some, we're not going to do an inner join because we would be dropping too many records, I think. I didn't even try an inner join, but I want the maximum number of records I can get and still have it make sense. I could do an outer join, but we'd probably get some nans and some non-matches, and that would just be more obtuse and more confusing. So we're not even going to go down that path. We're just going to stick here, okay? So we have the new data frame with the capacity right here, and matching on this, right, name. So we've got that. Now, lo and behold, look what we can do. We can have the station demand predicted. That's what we calculated a few minutes ago. Number of bikes available. That's what we got from the second data frame. Capacity, right? That's the total capacity for that array of bikes. There's 7 available. And we have a predicted demand of 8.76. That's what we calculated before. So this is going to go down to 1 and close to 0. We need replenishment, okay? So I did a quick analysis after merging the two data frames. This is a merged data frame. This is the head right here. So if you look close, we got that. That corresponds to this right here. But I'm trying to say, hey guys, do I need to replenish bikes at this source? Because a lot of people are demanding bikes. They're taking them away and they're not returning them fast enough to restore the supply, right? So we are way down on our capacity right here. We got 20, 7 available. Oh, I guess, yeah, it's not too bad, right? I think I misread that. 7 available. Demand is 7, so we'll go down by 1. It'll be down to 19. But still, we're getting kind of low. We probably need to replenish, right? It doesn't have to get to 0. That would be bad. We want to get to a lower number. And if we get down, it looks like it's half, right? So if capacity is 20, capacity is 20, and we have 7, we're less than half. We're expecting 8 bikes. Oh, I did read that. We had 7. It's going to go negative real soon. We can't have negative bikes per se. I'm sorry. But it's going to go down to 0 real soon. So this definitely has to be replenished. This has to replenish. This has to replenish, right? So this is what this report tells us. So I think that's pretty interesting, right? So that's one takeaway from this lesson. That's what I learned. I think that's pretty insightful. That's worth the money you spent for this video so far. You haven't even spent anything, right? So it's free, but that's worth a lot for the people that manage this program to say, okay, predicted demand's here, number of bikes available there, capacity is that, but we're going down to close to zero. We have to replenish the bikes ASAP. Guys, get out there, roll the truck, get the crew on the road, and start doing work. Okay. So that's the next part of this analysis. We know I just picked these um, locations over here, Park and Buffalo Avenue. I can't do a control find, I think, on the data frame. Oh, here it is. It's the first one. So that was lucky. So we have Park and Buffalo Avenue. I looked up the GPS coordinates for this and put that in here. So I'm going to put this into um, a quick geolocation, geodesic distance, GeoPy calculation engine here. And I'm going to go ahead and look at the differences here between all the routes and try to find the optimized route. So if I have to replenish the bikes, okay, so let me pause for a moment. It gets a little confusing, but it's not too bad. We can do this, okay? Stick with me. We have all the stations, predicted demand, number of bikes, right? Total capacity, but it's going down to zero. That is the maximum capacity. It's going to be at zero in about a minute, a couple of minutes here. We have to replenish the bikes. How do we go through all of these stations? We have 25. Remember, pick the top 25. I'm not looking at everything, single station in the whole ecosystem here. I'm looking at the top 25 based on the number of demand, right? So there is a method to the madness here. It's not just 25. It's the top 25 stations most in demand based on the time of day and the day of the week. How do we go through all of these 25 stations in the most efficient way possible? That's the question that I want to answer this. We can use SciPy Optimize almost like a traveling salesperson, TSP it's called, traveling salesperson, to solve this problem. I've got several videos on my channel about how solving the TSP problem. So we can go ahead and solve it. And we see the optimized route is 35.53 kilometers. Okay, so 35.53. If we just ran through kind of randomized, I mean, they could do it not randomized fashion, but if you don't optimize, it is considered non-optimized by default. That's the definition of not optimized route. Either it's optimized or it's not. And it's going to take a lot longer. So here, when we optimize it and we go through the most efficient route, this is going through all the paths on the whole system, and replenishing all the bikes that we need to replenish, but doing so in the minimum distance possible. And of course, by default, the minimum time possible, burning less fuel and less resources, right? There's already a problem on this planet with global warming. If we can use less fuel and do the job faster and just in optimized fashion, why would you not want to do that, right? So 3 times 2 is 7, times 2 is 14, times 21, almost 5 times longer or 5 times more distance if you kind of randomly just go around, oh, let me put some bikes over here, put some bikes over here. We're going to get the top 25, but there's no specific pattern that we're going to do it in. This is called a random walk. You see this on Wall Street sometimes when stocks move up and down and the prices move randomly. This is called a random walk almost. So you see this in a couple different industries or a couple different sectors, like demand, any kind of demand forecasting, really, and an optimized solution, right? So here's the optimized, almost 5 times more efficient than this, which is not optimized. So let's look at one more solution over here. Now I have a Google Places API key. I'm setting up the analysis to be a little bit different, going to all these places. I think this was super optimized. And I think what it's actually doing, because this route is almost like too good to be true, you don't see it on the map because I didn't even plot it, but what it's doing is putting straight lines between all of these different beginning and ending points. So the problem is that you can't drive in a straight line, okay? Now, like we all learned in math school, the shortest distance between 2 points is a straight line. Go from A to B, B to C, C to D, and so on and so forth. It's a straight line. But in reality, you don't follow a straight line. You follow the contour of the road or the pattern of the road and the street, okay? So you're driving the street twists and curves and it swerves back and forth. You have to follow the pattern. You're not going in a straight line most of the time. So this is a straight line solution. That's great. Realistically, we're not flying there. We're driving. So we have to follow the route of the street. So when you follow the route of the street, and by the way, you can get your Google Places API key for free. If I go over here, I can go to Google Console, GCP is called Google Cloud Platform, Google Places, API key. You can get it for free. It takes maybe a minute or so to set up. It's very quick. Go over here, Google for developers, use API keys with Places. I've got several videos on how to do this. And I think, is this right? Let me see something here. I want the console. That I don't think is right. Okay, sometimes You have to hunt around and peck around for this thing a little bit. Manage API keys. This one sounds right to me. Okay. So if you go over here, no, still not. Still not getting there. I want the console. I see it. It's over here. Okay. A lot of these things are linked. So if you go to your console, I'm already logged into mine. So the first time it might take a little bit of time, but it's pretty quick. Maybe a minute, maybe less. Go over here to APIs, and you'll have your Google Places API. And it's pretty cool. You can get all kinds of restaurants, entertainment venues. It'll find anything, coffee shops, bowling alleys, whatever your thing is. Like Google Places has all the details, right? So it's great for that and for planning distance between endpoints, right? So here's one, here's another, here's A, B, C, D, E, F, G, so on and so forth. So here's the top 25 addresses, again, by bikes being demanded at each place. So I'm going to find the optimal route for using SciPy to find the shortest distance between all of those, okay? And when I go ahead and solve that problem, I'm going to show you the non-optimized problem, right? So if you just go randomly between one point and another and another, and all the guys on that crew driving the truck go out and put back all the bikes or resupply the numbers of bikes at all these stations that have been depleted. If it's random, it's going to take a lot longer. We just saw that. So here is the first driving point, 14.73 miles, 24 miles, kilometers, 82, 94. So it's cumulatively increasing, right? Until we get to 381.08 kilometers, okay? So that sounds like the non-optimized. If we zoom out, we can see everything on the map. And again, remember, it's following the routes. It's following the routes of the street. The first one you saw a little while ago was fine, just doing straight lines. But realistically, we're not flying between bike rental stations, right? We're driving the truck with a bunch of bikes parked in the back of the truck. I've seen these guys going around the city. So they have to follow the streets, right? That's the only way you're going to get around Manhattan into the Bronx. You can see Queens and Brooklyn over here. You have to follow those routes. When you do that in kind of a non-optimized fashion, it works out to about 381 kilometers. That's a lot of kilometers, guys. If you optimize it and go in this order, you do this one first, that one next, down to here. That's the last one. And then you're done 103 kilometers. So 3 times shorter, presumably 3 times faster, 3 times less gas. Oh, almost 4. Look at that. 3, 8, 1. And down here, it's just over 100 kilometers. So you can decide for yourself. I will take the 103 any day of the week. Faster time, less gas burned, easier on the crew. You're not driving all over. You're not taking the scenic route. You're taking the optimized route. Okay, 103 kilometers and you're done. These guys over here, God forbid, if they don't know what they're doing, they're going to take 381 kilometers to do exactly the same job. Hopefully I'm not riding with those guys. I don't want to be on that truck that's low. Windshield time. I used to work for a company, they call that windshield time because you're staring at the windshield so much, right? Okay, so let's wrap up the analysis. I'm at 33 minutes. I promised I would keep it short, and I swear I'm doing the best I can do. It's just lots of stuff to get through. So that's it. So we sorted the demand. We calculated demand using the regression model, right? Random forest regressor. Based on demand, we know how quickly or how slowly different bike racks, or what they call it, different bike tracks or whatever will be depleted. Those racks where the bikes are held, right? So we know how quickly the numbers go down, and they have to be resupplied if people don't do it themselves. Sometimes people do, but a lot of times they don't. So you need that truck driving around the city, replenishing all those bikes. So we answered that, and we did an optimization problem down here, traveling salesperson, and we saved 280 kilometers off the route instead of 381 over here. We did the whole thing exactly the same route and accomplished the same mission in 103 kilometers, right? So that's very nice. And last thing I'll leave you with here is just a little bit of sample code. If there's some chance that you want to download all of these files automatically into a folder and then concatenate all those files together, you can quickly and easily do that using this code. I downloaded all the files, unzipped them, and cleaned them up, and I got this. This is pretty massive. It is 3.47 gigs on my hard drive. I tried to merge several of these files, and after a few minutes, the code just crashed and said it ran out of memory. So my machine doesn't work, but I'll gladly give this code to anyone that wants it. You can download all the files from this base URL over here. Right, just put everything you want in that list. The code will go through everything in the list. You can tell it's a list because you have the square brackets. Right, so file names is the name of the list. And if I put that down here, we're looping through items on the list, right? So loop through all the items, download all of those. And if you're interested in concatenating all those files into one master file, you can do that with this code. So this go through those 12 files, open each one, scan through it. Now, in this case, I'm actually only getting the first 10,000 rows. Number of rows equals 10,000. So I did scan through it to test it, and I got 1.2 million rows. 120,000 rows, 10,000 from the 12 files. I got 120,000 rows. So I got samples from all those months. So I have September, October, November, December, and January, starting from January down to December. So I have all those months. So we don't see only July. If you want to do that type of analysis, this code will concatenate everything together. So you have all the months, you have all 12 months. I tested it just with 10,000 rows and it worked fine for me. I just went with that one file in the end. Over here, come on, mouse is misbehaving. I went with this one in the end for my analysis. But if you want to do all 12 months to get 10,000 rows from all 12, you can do the same thing and everything will line up. You'll just get all the months. That's the only difference. So that's it. Hopefully this was enlightening and informative and helpful for you guys. I like to do these things. I like to dig in and see how this works. It's always a new learning experience for me, and hopefully it is for you too. So I'm going to wrap it up right here, and I'll see you guys in the next video. Take care. Bye.